Parallel coordinates is a versatile visualization technique that can be applied to almost any multidimensional tabular data. Additionally, parallel coordinates affords this interaction of brushing along the various dimensions, which enables this thing called multidimensional filtering, where you can specify a min and max value for multiple dimensions or attributes of the data. This particular example represents a lot of my thinking and iteration on this particular example over the past couple of years, actually. So instead of walking through the step-by-step process of building it, I'm going to just explain the code that already exists. Here's the code in VizHub, and I'll just walk through what it's doing. This implementation is heavily inspired by this implementation of parallel coordinates in Observable by Mike Bostock, and also this example, which has brushing. The main difference between those implementations and this implementation is that this one uses vanilla JavaScript and unidirectional data flow. So we pull in a bunch of things from D3, we import the iris dataset. That's what this is. Each row of data represents an iris flower that has sepal length, sepal width, petal width, and species. We also pull in observe resize, which we use to make this example responsive. See, if you resize it, it responds to resize and also changes in the browser zoom. And then we import parallel coordinates from this file, a local file. And let's just take a look at how we invoke that. We assign a unique ID to each row, and we'll see later why we need that. We also list out the columns and the column types. This is important because the quantitative columns need to use a linear scale, but the categorical column, species, needs to use a point scale. And then we use the same pattern that we've used in other places to define value accessor functions for color and ID. So here's the main function. It takes as input the container, the DOM element, and state, and set state. This is the incantation to make it responsive. And we set up our top level SVG with pretty familiar looking code. And then we use .call to invoke parallel coordinates with all these various things and brushed intervals from state.brushedIntervals. That is an object that represents the state of all these brushes combined. And initially this is undefined, so in that case we fall back to an empty object. That probably just simplifies some downstream code. And then here's an implementation of a function called update brushed interval. Whenever a brush moves, we call this function. And this function takes as input the column, which is one of the entries from columns, a string, and the interval, which specifies the minimum and maximum values for the brushed area. And this uses immutable update patterns to update the state to be all the properties on the previous state plus state.brushedIntervals. And here it's using a nested version of this immutable update pattern by taking all the existing properties on brushed intervals from before and putting this new interval associated with this column. And this syntax, by the way, uses the string value of column as the key for this object. As with any more complex interactive example, the state of it is sort of the central piece. So understanding the shape of the state is critical for understanding how this thing works. To that end, let me just console.log state.brushedIntervals so you can see what this looks like over time. See, what we get from console.log state.brushedIntervals is an object where the keys are the column names and the values are arrays of two elements, the maximum and minimum brushed interval. And if I change this over time, Well, actually, with this format, it's hard to see, but let me just json.stringify state.brushedIntervals. Now we can see a little more clearly how these things update. Or even better, null and 2 to format these. So now we can see that if we remove a brush, or remove all the brushes, we end up with an empty object. And if we add one brush here, it just has one property corresponding to that column. And if we add another brush, it has two properties. And this data structure is expandable to an arbitrary number of attributes that we can filter on. All right, that's the shape of the state with state.brushedIntervals. Now let's take a look at that parallel coordinates implementation. So we are calling that parallel coordinates function, which is imported from this file, parallelcoordinates.js. Let's start by looking at the core implementation that renders the marks. Now this logic is a little bit complex because it's made to support animated transitions. Notice how the lines fade in and out as they get added to or removed from the filtered set. This more complex code is required to support that kind of interactions. Here we set up a transition of duration 500 milliseconds with ease linear. That is the transition that powers these fades. So see, if we make this something like 50, the fades happen instantaneously pretty much. But if we make it something like 5 seconds, these things take a long time to fade in and out. So that's what that duration controls. And then we say selection.selectAll path.mark. That selects all the paths that have a class of mark. And I'm using this class of mark just to disambiguate between any other paths that may be on the page. And then we say .data filtered data ID value. Filtered data is the data that is filtered by all those brushed intervals. And we'll look in a second how that's computed. And the second argument is the ID value. This ID value is critical for telling D3 which of these path elements correspond to which of the data elements on a consistent basis. If we leave this out, D3 will use the index in the array as the identity. And look what the effect is there. The transitions are all messed up because whenever the number of things change, the index of a certain row changes because we're changing the length of the array. We're filtering it every time. So that's why, it's super important in this case when you have transitions like this to include the ID value as the second argument to .data. And then here we have the long form of .join, which handles enter, update, and exit separately. On enter, we append a new path with a class of mark, and we set the opacity to 0. This makes it invisible at first, and then we use .call to kick off a transition that transitions the opacity to 1. So this is why on page load, it will fade in. And in general, when it enters, it fades in. So this fading in part is controlled by that code that we just reviewed. It fades in when it enters and comes into view. And this update part is a little confusing. I mean, it just sets the opacity to 1 with a transition. And it may not be clear why we need this. So let me show you what happens if we don't have it. If we apply a no operation for update, let's see what happens. We get these weird bugs where these things are not properly entered, or not all the points under the brush appear when you move it back and forth. Now, why might that be? Like, what is going on there? This part took me a long time to figure out. And let me slow down this transition to make it easier to follow. This class of bug actually depends on this exit thing. What happens on exit? So when these points fall out of view and are no longer in the brushed area, exit gets invoked. And for that, we kick off a transition that keeps them around for the duration of this transition and transitions their opacity to 0 and then removes them. Let me highlight for you the cause of this mysterious bug. Take a look at these points here. When I drag this brush like so, all of these lines start fading out, right? And if I let them fade out to completion, those DOM elements get removed. And then when I brush on top of them again, they come back. No problem. Here's where the problem lies. If I brush like this and they start fading out, but then I brush over them again, and they go into the set of things that should be shown before the DOM elements have been removed, they fade out, and that's the bug that we're up against. And so what happens is, in reality, what we want to have happen is that when they are, here, let me move to the next row. When they are fading out and we brush over them, that actually triggers the update case. So that's why in the update case, we must transition their opacity back to 1. This is related to the concept of transitions being interrupted. See, with the 3 transitions, there is the notion of interrupting a transition. And so when the exit case gets called and we kick off the transition to transition its opacity to 0 and then remove it, if that same data point is then added back into the set of things that we want to show and update gets called, we actually kick off a new transition on the same DOM element, and that interrupts the previously ongoing transition, which was about to remove it. And so after we interrupt the exit transition, it will never get to the end, and it will never remove that element. And that's exactly what we want here. Okay, so now that this call to update is back, we can do something like this, where we trigger the fade out of all these other ones, but before they faded out completely, if we brush over them again, that fade out transition is interrupted, and then a new fade in transition is kicked off, and those lines within our brushed region are visible. So this is the setup where there is what I like to think of as eventual consistency. Like eventually, all the lines inside of our brushed regions are visible after all of their fading in and fading out. So that is the join longhand notation that you need for a bug-free fade in and fade out set of transitions in response to data that gets filtered. The rest of this example is relatively straightforward. I think the most interesting part may be the filtering of the data. Filtered data is being used here to drive these marks, and let's see how filtered data is computed. Hey, we're actually memoizing it. Memoization is a form of optimization where you only recompute something when it's necessary to recompute it. This is such a small data set where we don't really need it, but I just wanted to do a proof of concept for how we do memoization within the context of unidirectional data flow. So I will first explain the core logic of the data filtering, and then I'll explain about what memoization is and how this function works. So filtered data ultimately is computed by this code here, which uses data.filter, which is a built-in method on arrays, which returns an array of the filtered data, meaning if this function returns true, then that element is included in the filtered result, but if this returns false, it is excluded from the filtered results. This function here checks if a given row, D, should or should not be included in the filtered set. And the way that it checks that is it loops over all the columns of the columns array, and this is just an array of strings that's defined here. It's just the array of column names, which can be used as keys for the row objects. So for each of those columns, we look up the interval that is currently brushed for that column, and that's from state.brushedIntervals. If interval is defined, and by the way, interval may not be defined, like if we don't have any of these things brushed, interval is undefined for all these cases. Because we're looping over the columns, we're always checking if each and every column has a brush defined, and so this will be undefined sometimes. And if it is undefined, then it'll just skip over this and go all the way to the end and return true. Because after all, the role of one of these brushed intervals is to filter out a certain subset of points. But which subset of points? If the interval is defined, we unpack it using ES6 destructuring on arrays to get the max value and the min value. So the max value is here at the top of the brush, and the min value is from the bottom of the brush. Once we unpack the interval, we get the actual value out of the data for that column. So like, for example, a sepal width of, I don't know, 2.5 or whatever the value may be. And this check here determines if this row is filtered out by this brushed region or not. So if the value is less than the minimum, meaning it falls on this side, or the value is over the maximum, meaning it falls on this side of the brush, then this function returns false, essentially short-circuiting, not checking any of the subsequent columns because we already know it's been filtered out by this one column, and it returns false out of this function, excluding that row from the data. So if a certain row gets through all of these filters, we return true because it hasn't been filtered out by any of them. And this logic scales across all the columns in such a way that it performs an AND operation, because if it's filtered out by any one of these brushes, then it's excluded from the whole set. And so this is what powers this interaction of being able to drill down into very specific multidimensional filters. Okay, that's the core multidimensional filtering logic. Let's take a look now at this memoization concept. This is very much inspired by the useMemo function from React, which lets you cache the result of a calculation between re-renders. This is a commonly used performance optimization that lets you avoid expensive calculations by checking if the dependencies change. And a dependency is anything in the upstream code that that calculation depends on. What I've done here with this memoize implementation is made it pretty similar to useMemo from React, in that the first argument is the function that computes the memoized value. And then the second argument is the array of dependencies, just like in React. This is a list of all the things that are referenced in this code, such as data, and data doesn't change that often. It actually doesn't change at all. It just gets loaded once and doesn't change. Columns, that also doesn't change. The only thing that actually changes in our case is brushed intervals, and that changes whenever you modify the brush. So let me show you what this actually means. I'm going to bring back this console.log and say, it's going to say recomputing filter data every time this code executes. All right, here I've got the DevTools open, and I've got it running full screen here. And two of the things we can do that change the state are brushing and resizing. And the whole point of memoization is to only recompute the filtered set when the brush changes, but not when you resize the page. So check this out. Every time I brush, it says recomputing filtered data. And then if I clear the console, but then resize, it's logging out that other stuff, but it's not logging that it recomputed the filtered data. This is the point of memoization. Some expensive calculation can be essentially cached based on its dependencies. Let's take a look at how that's implemented. And it's worth pointing out that the third argument is selection.node, which is the DOM element. Because unlike React, which somehow knows about, it can infer what thing to associate it with what other thing, but since we're not in the context of a giant framework, I'm just attaching the cached values to the actual DOM node. And that supports memoization with hot reloading. And this memoize function is actually just imported from /memoize, which is defined right here. The implementation is not that long. It takes as input a function, the dependencies array, a DOM node, and optionally a name in case you want to memoize multiple things on one DOM node. And so we compute a property to put on the DOM node as underscore memoize dash name, and then we get that value off of the DOM node, which may or may not exist. So if the memoized value exists and the dependencies haven't changed, at least their length hasn't changed, then we figure out if the dependencies actually changed by initializing this variable dependencies changed to be false. And then for each and every dependency, we check if the dependencies, like the latest version of the dependencies at that index, is different from the previous version of those dependencies, which is stored on the DOM node. And this uses object equality. So if you redefine the same object that is essentially the same as it was before, it will be counted as different. So you have to memoize things all the way up the chain, so to speak, just like in React. So if it's different, we know the dependencies have changed and we break out of this for loop. And if the dependencies have not changed, we just return the memoized value. So if we get through all that, it's either the first run or the dependencies have changed. So in that case, we invoke the function, which computes the value, and then we store an object with the value and the current version of the dependencies on the DOM node, and then we return the value. That's how I, at least, implemented memoization in vanilla JavaScript, similar to the way React does it, in a way that supports hot reloading. Lastly, let's take a look at how these brush interactions are actually set up. In parallel coordinates.js, we have brush y. This defines a vertical brush. We set the extent of the brush based on a variable called brush width that defines how wide the brush is and the height available to us. Oh, come to think of it, it should probably be capped at the margins. So let me just quickly modify that. There should be margin top and height minus margin bottom. Now it caps at the bottom, which is, I think, correct. Yeah, more correct. Anyway, that's how we set up the brush Y, and then we add these event listeners. Brush start, meaning the brush is, I guess, initially set up. The brush event, which happens when you just drag the brush, and then the end event, which happens when you get rid of the brush. These events take as input the selection and the source event. Oh, and we are programmatically moving the brush, which is crazy. So yeah, if you brush, check it out. If you brush and then resize, it actually programmatically updates the position of the brush to be correct. So there's some logic around that, where if the source event is true, meaning it was actually a user interaction, then, and only then, do we call update brushed interval, passing the column and the interval. And the interval is selection, which is the pixel coordinates, min and max, dot map, Y scales at this particular column dot invert. So scale dot invert will actually figure out the data value that corresponds to the pixel value. And if there's no selection, then we return undefined for the interval. And that's what happens if you get rid of the brush. And this depends on Y scales being set up. Let's take a look at that. So here's Y scales, and just for each column, we define Y scales at that column to be, is the column type quantitative? If so, we set up a linear scale based on the extent and the margins. Otherwise, we use a scale point using data.map for the domain, which isolates all the unique values, for example, these 3 species values, and then we set the range based on the height and the margins. So that's basically it. That's pretty much how it works. I'll just quickly go over the rest of the code that I missed, but from here on out, it's all relatively straightforward. For the color scale, I did this neat thing with this hue shift, where I just took the, see the colors? See the colors there? I just took scheme category 10 from D3 and then applied a function to make them look cooler. I was just feeling a little bored with the defaults. So hue shift is just a neat little function that uses D3 HCL, which is a hue, chroma, luminance, color scale, or color space from D3. And it just shifts the hue and returns the new color. So that's how we get these neato colors. Oh, and here's the code that actually calls all those brushes. We append a group, a brush group for each column, transform it by the X scale of that column to move it over into the right place, and then we use .call brush. And then this is the bit that programmatically moves the brush when the window is resized. This took me some time to figure out. So if the brush interval for that column exists, then we call select this, which selects the particular group element, .call brush.move, which is a way to programmatically move the brush to the proper brushed interval, which we get by accessing brushed intervals at the column, which gives us a 2-dimensional array, the max and the min, which we map over because that min and max is in the domain of the Y scale, and to get it back to the range, we need to pass it through the Y scale for that column. And that's because brush.move accepts the pixel coordinates, not data coordinates. And then we add an x-axis, which is pretty typical. That just sets up these labels here. Did a couple customizations like setting the color, setting the font size. Using a custom tick format, that just replaces the underscores with spaces because I didn't like the way that the underscores looked. And then we set tick padding, which determines how far away those tick marks are. And then I did a little additional work to remove some extraneous paths and lines, which I didn't think were required. See, if we bring those back, there's like this line there and those tick mark lines, which I thought were a little ugly, so I got rid of them. Last but not least, notice how when there are overlapping lines, they become sort of brighter, and it gives kind of a neon effect. This is a fancy schmancy technique using mix blend mode, where I set it to be screen. See, if we don't put that, it looks pretty flat. It looks relatively flat just because it's using the straight colors. But if we bring back mix blend mode of screen, it kind of pops out a lot more. Hey, I never actually talked about how we computed the line, the D attribute. Well, here it is. D, which is the path string, is generated by this line generator. And let me just see how that is defined. Okay, line generator is an unconfigured instance of line imported from D3. When setting the D attribute, we use line generator, and we pass D into that function, and D is one of the rows from our original table. So for each row, we map over the columns, all the columns that we want to show. So for each combination of row and column, we generate an array that has 2 elements. And this is what the unconfigured line generator uses. It expects an array of x and y coordinates, and we derive the x coordinate by passing in the column to the x scale. And let's just see how the x scale is defined real quick. X scale is a scale point where the domain is all of the columns that we're using. So that's what spreads these across. So that's how we compute the x coordinate of each of these points along the multi-line. For the y coordinate, we look up the y scale for that column, and then we pass in the value of that column on that row. So that generates an array of these arrays with 2 elements, array of coordinates essentially, that gets passed into the line generator. So that's how we generate each and every one of these multi-line paths. All right, that's how you can do parallel coordinates with brushing, multidimensional filtering that's responsive. A challenge for you: fork this visualization and put your own data into here. You'd be surprised at how versatile this is. It fits with most datasets. Good luck.